We're going to try and use this as a way to explain how to solve an example problem. This is quite complex, but we're hoping that this will help us to explain this particular example. This is from Chapter 8 Statics. It's from the section on couples and it's question 6. The text is up on the left here. ABC, equilateral triangle, side L, forces 8, 8 and 4 newtons in the direction shown. We have to calculate the magnitude of the resultant, then the distance from A to the line of action of the resultant, and then there's a further question here about reducing the forces to a single force and couple. So sticking with the main problem, let's calculate the magnitude of the resultant. We need to look at the geometry, so here's one we prepared earlier. If we look at the equilateral triangle divided in two by the vertical red line, let's see, we might be able to show that here, the vertical red line here, then that gives this triangle here. This is what is represented here. So in that case we have an unknown length x, which corresponds to the height of this triangle. We have the length L, and this will be a half L, since it's half the length from A to B, half the length of the equilateral triangle. So working through, we find that x then is equal to the root of L squared plus a half L squared, Pythagoras, and that's root 3 over 2 times L. Let's move on to the next slide. And so we see that AB here, AB here, AC there, and BC. This is a little more complex again, but we have the basic idea that we can take those vectors AB, BC and AC, let's just go back, can be described in this way. So we have AB is straight across in the positive I direction, it's equal to 8I. We have BC, which we can resolve as minus 8 cos theta I plus 8 sin theta j. That gives us minus 4I plus 4 root 3j. And finally we have AC, which gives us 2I plus 2 root 3j. We can add those to give us the resultant. In that case, we have 8 minus 4 plus 2I and 0 plus 4 root 3 plus 2 root 3j. That gives us the 6I plus 6 root 3j, and when we calculate the magnitude, that gives a magnitude of 12 newtons. So we have a resultant which is 12 newtons in magnitude. Let's have a look at the geometry. That vector r then, given its plus 6I plus 6 root 3j, would be in the direction shown roughly here, pointing in this direction. That means its line of action, the perpendicular distance to the line of action from A, will be given by this distance d. Now AC goes through A, as does AB, so they will have no moments. The only force over here which does have a moment is the 8 newtons from B to C. However, we need to identify the distance of its line of action from A. So to do that, we need to look at the geometry again. This is the same equilateral triangle. This time we have divided it in two as shown, and the length of the dashed line is x. That represents the distance of the line of action of the 8 Newton force BC from the point A. So we work out x, it's the root of L squared minus L squared over 4, and that resolves to x equals root 3 over 2L. So that x is the distance of the line of action of the force 8 newtons BC, and that must be equal to the size of the resultant r times the line of action d. So we have moments about A, the sum of the moments is the moment of the sum. So again, moments about A. We have r, the resultant, times d, the distance of its line of action from A, equals 8 times the value of x. But we have already shown that x here was equal to root 3 over 2L. So we have 12d equals 8 times root 3 over 2L, and that reduces to the distance d is L over root 3. The final section of this problem says if we assume that the force is replaced by a couple. Well, the sum of the moments from before was 8 times root 3 over 2 times L, which gives 4 root 3L. Therefore, that must be the size of the couple moment. Perhaps we need to explain that a little more, but we'll leave that for now.